Okay, so this is a recording for the 424 course. This is a topic in input modeling, and this is a continuation of what we already started in class. We are going through the four steps in order to define our models for our simulations, our input models for our simulations. And we are currently discussing how to estimate the parameters once we identify the distribution from our data. Okay, so the last thing we did in class was to discuss this table. In this table we have the parameter estimation for some of the probability distributions we discussed in class. For example, we have the Poisson. So in order to estimate the Poisson parameter, which is here is identified as alpha, we need to compute the sample mean. Okay? So what I'm going to show you now is an example in how to estimate the parameters for the gamma distribution. So for the gamma, we need the shape beta and theta parameters, and I'm going to show you now how to compute those parameters. So this is the example. Suppose that lead times associated with 20 orders follow a gamma distribution, and we want to estimate the parameters based on the data that we have. In this particular example, we have 20 data points, and we have a lead time in days for each one of those data points. Okay, so based on this information, we need to estimate the parameters for the gamma distribution. So in the table, the table lists theta as the estimation of theta. You need to compute the sample mean, and then look for 1 over the sample mean to get the parameter estimation for theta. For beta, we need to do something else. So we're going to start by, I'm going to show you first how to compute theta. So this is very simple. What you need to do is to compute the sample mean. And you know that the sample mean is just the summation of all your data points divided by the number of data points that you have. So in this case, the summation is equal to 564.32, and we have 20 data points. So X bar equals 28.22. Okay? Now, in order to estimate theta, we need to look at theta hat is going to be equal to 1 over X bar. So in this case, we have 1 over 28.22, which is equals to 0.035. Okay? So this is the first parameter. For the gamma distribution. Now, we have to estimate the second parameter, which is beta. And in order to get this parameter, we need to refer to table A9 in the appendix of your textbook, because there are some tabulated values there that we're going to use in order to estimate this parameter. So for beta hat, use table A9 from the textbook. And the first thing that you will have to do is to compute the value for m. So m is going to be equal to the logarithm of x bar minus 1 over n, the summation from I equals 1 to n of the logarithm of each observation. Then you have to compute one over m. Okay, so we need this value 1 over m in order to use the table that is presented in in the appendix of your textbook. So let me show you that table really quick. So this is the table I'm referring to. So in order to get the estimated parameter for beta, you have to compute 1 over n. Okay, so let's compute that value. So let's go back to the slides and let's find the value for 1 over m for this case. So if you solve this expression, m would be equal to 0.14 and 1 over m is equal to 7.14. Okay? Now using this value, we can refer to the table and we're going to have to use interpolation in order to get the value for beta hat. So use interpolation. So if we go back to the table, we know that our value for 1 over m is 7.14. So we need to find that value here in this table. So if you go up to this point, you'll see that that value is within these two numbers. So the value for our beta hat is between 3.65 and 3.80. So we're going to use interpolation in order to find the exact value based on these numbers. So let's go back to the slides. So we have those numbers, so I'm going to interpolate between those ranges. So we go 7.14 minus 7.0 divided by 7.3 minus 7.0. This has to be equal to x, and x is the value that we need to find, beta. X minus 3.658 divided by 3.808 minus 3.658. And if you solve for x, then you get that x equals 3.728, and that's the value we're looking for, which is our beta hat. So for these data points that we know that follow a gamma distribution, the parameters for that gamma are theta equals 0.035 and beta equals 0.03, beta hat equals 3.728. Okay, so this is an example of how to estimate the parameters for a gamma distribution, and also shows you the importance of referring back to the table in order to know what type of computations you need to perform in order to get the parameter for the distribution that you're looking at. Okay? So that covers the third step in our input modeling procedure. Now we're going to move to the fourth step, which is the last one. And in the fourth step, what we're going to do is a goodness of fit test to basically test our hypotheses in terms of identifying the distribution. Okay? So for this, we're going to conduct a hypothesis testing on input data distributing using these two tests that you already know, the KS test and the Chi-square test. Okay? Again, no single correct distribution is real application. In a real application exists. So if very little data are available, it is unlikely to reject any candidate distributions. Now, if a lot of data are available, then it is likely to reject all candidate distributions. Okay, so this is a trade-off. So if you have only few data points, it's going to be very hard for you to find a distribution based on the information that you have. But if you, on the other side, if you have a lot of information, then again it is likely to reject all candidate distributions. So we're going to start by discussing the Chi-square test. So as an intuition, what we're going to be doing with the Chi-square test is comparing the histogram of the data to the shape of the candidate density or mass function. So a density function is used when you have a continuous distribution. A mass function is used when you have a discrete distribution. And this is valid for large sample sizes. So for the chi-square, by arranging the n observations into a set of k-class intervals or cells, the test statistic is this one, the chi-square observed, that you already know. where OI equals the observed frequency, EI is the expected frequency, and this is going to be equal to n, which is the number of observations times the probability, pi, and pi is the theoretical probability of the ith interval for the expected frequency. The suggested minimum for this chi-square test is 5. So suggested minimum equals 5. Okay? This approximation follows the chi-square distribution with k minus s minus 1 degrees of freedom. Okay? So the approximation follows the chi-square distribution with k minus s minus 1 degrees of freedom and s is equal to the number of parameters estimated by the sample statistic. Okay? So now using this information, what we're going to do is to perform a hypothesis test. So our null hypothesis is the following. The random variable that we're going to call x conforms to the distribution assumption with the parameters given by the estimators. And our alternate hypothesis is the random variable does not conform. Okay, so remember what we're trying to do here. You have a group of data that you collect from the system. You're using that group of data to identify a probability distribution that you can use in your simulation model as an input model. For example, if you're looking at the processing times for a machine, you're collecting data from the processing time of the machines, how long it takes that machine to complete a particular part. You collect 100 data points then you use that information to try to fit the distribution. So basically, you plot that information using a histogram or a QQ plot, and based on what you're seeing, then you can make a guess in terms of the distribution that those data points are following based on the shape of the data. Now, after you make that assumption, then you need to estimate the parameters, which is what we did. You estimate the parameters based on your assumption. And what we're trying to do now is to test that hypothesis that you made in the first place to see if statistically that assumption is correct. So we're going to use the Chisquare test and also the KS test in order to test your assumption based on the data points that you collected from the real system. Okay? So we do this hypothesis test for the chi-square, and now we need to differentiate in terms of the type of information that you are collecting. So if you identify a discrete, or if the distribution tested is discrete, and combining adjacent cells is not required, then each value of the random variable should be a class interval. Okay, so this is for in the case that you identify a discrete distribution for the data points that you collect from the system. Okay, and Pi is going to be equal to the probability of xi, which equals the probability of the random variable being equal to xi. Okay, now if you have a case in which the distribution tested is continuous, then you have to estimate that probability Pi in a different way. So Pi is going to be equal to the integral from ai minus 1 to ai of f of x dx, which is the same as looking at the cumulative distribution evaluated on ai minus the cumulative distribution evaluated at ai minus 1. So this is ai minus 1. Okay? So where ai minus 1 and ai are the endpoints of the I class interval and f of x is the PDF that you are assuming. Okay? So in terms of the number of class intervals that you're going to need for your test, for your chi-square test, here I have a table of the recommended number of class intervals that you can have based on your sample size. So if you have 20 data points, so if n is equal to 20, do not use chi-square. Now if you have 50, you can have from 5 to 10 class intervals. If you have 100, you can have from 10 to 20. And if you have more than 100 data points, then you can use this relation n, or the square root of n, to n over 5 class intervals. Okay? So as a warning, or you need to be aware that different grouping of data can affect the hypothesis testing results. Okay, so two different cases, one for the discrete. In the case for the discrete, you have that each value of the random variable should be a class interval. For the case of the continuous,
I'm sorry.
you have the probability has to be computed based on the integral for the continuous case, for the continuous case. Okay? So the next thing we're going to do is to compute the chi-squared, or to use the chi-squared for a discrete case. And I'm going to save the video here, and we're going to continue on the next video.